So this topic here is on something called relative motion. And I usually make some sort of really corny joke about how relative motion ruins the punchline.
Can I get
Bill.
any grade 10, 11, or 12 students?
Love the reverb for their hair.
The Our School survey, come to room 126. That's grade 10, 11, and 12 students who have not done the Our School survey. Please come to room 126. Thank you.
Now you ruined my joke. I always make some sort of lame joke about how relative motion is about how, like, when you're in a car with your family or something like that, but it got ruined. Okay. Thank you. I got a better groan from even that than I did first block. Let me try to describe relative motion to you in a scenario not the one that's on the page here. If I were to ask you right now how fast you're moving, you'd say, Chris, I'm not moving. I'm sitting still in my desk. And I'd say, well, that's not really true because you're on the Earth, and the Earth is moving through space. So therefore, you are moving. Do you understand kind of the weird scenario that's going on there? That's how relative motion works, is it really depends on where you're considering your vantage point. From me to you, you guys don't appear to be moving. But let's say that I was sitting on Jupiter, and I was watching you from Jupiter. Well, then you'd appear to be moving because the Earth would be moving relative to Jupiter. Does that make sense? Let's say two friends were walking down the hallway side by side next to each other. Relative to each other, you're basically going the same speed. So you can kind of say, well, I'm always just next to my friend. But someone who's watching you from somewhere else would say, well, no, you guys are moving. Right? Use this diagram right here as an example. Say you're taking a look at this person standing on a train. The train is moving to our left at 40 miles per hour, but there is a person on the train walking backwards the other ways at 10 miles per hour. Now, if I was on the train, I would see the person on the train walking 10 miles per hour. But if I were standing on the sidelines, watching the train and person moving, how fast is the person moving to the observer on the sidelines? Anybody know? Say it. They're traveling 30. Yeah. Because even though the train is going 40 that way, the person's walking the other way at 10, they would kind of cancel each other, and you'd see them moving at 30. And so we call these terms the relative motion and the apparent motion of objects. And it really depends on your perspective. If you are on the train, you see a person walking at 10. But if you are off the train, you see a train moving 40 and a person moving 30. Okay. Let me give another example. Let's say that I was to throw an object. Let's say that I was throwing a ball through the air and I was standing still. Okay. Well, the initial velocity of the ball would be whatever I throw it at because I'm standing still. But let's say that I was running in the direction that I was throwing and then I threw the ball. Wouldn't the ball be going just a little bit faster because I'm moving in the direction that the ball was traveling? Right? Or another sports analogy. One of the hardest shots, Michael Jordan was the best at it, was the fade, like the jump back jumper, right? If you're just going straight up and down, you have to shoot the ball a certain distance into the net, right? But if you're fading back, you have to shoot it just a little bit harder to make up for the fact that you're going backwards as you're doing your, like, fade away. I just about fell there. Does that make sense? Let me try another example on the next slide here to make sure I'm illustrating this concept well. Here's a cartoon I found. There's a person standing inside this railway box of some kind, and the person says, I'm standing still. But the person outside the box says, wait, hold still, right? They have different relative motions because this person right here thinks they're standing still. But if the railway car is moving, they're moving. Does that make sense? The person that's on the outside looking at them, seeing them, says, well, hang on, I see this person is moving. So your perspective makes a difference. I gave a really silly example to my first period class. I suggested that, say a police officer pulls you over and says, how fast were you traveling? And you cheekily say, I wasn't moving at all because I was sitting in my seat in my car. My apparent motion was 0. I probably wouldn't do that because the cop's not going to be happy with you being a little smart aleck. But do you get the idea there? Because to the cop who's watching you from the outside of your car, you were traveling, say, 60 kilometers an hour. To you, the person sitting inside the car, you weren't actually moving. Now, here's the thing, though. We recognize this already. Like, people already understand the concept of apparent versus relative motions. Right? But in physics, it makes it a little bit challenging because the math is not going to be any different. We're not going to use new formulas, but you have to recognize what velocity you should be using. Should you be using the velocity of what you feel like you're traveling? Or should you be using the velocity of what somebody else sees from the outside you traveling? That makes sense at all? Let me try some examples. I'm going to sit on the other side actually here. Here's my first example I want to try. It's a boat going across a river. Okay? And so if you can kind of imagine this scenario here, there is a boat that wanted to cross this river right here, straight across. And the boat is able to travel 1 meter per second, which means that straight across the river, this guy was traveling 1 meter per second. However, there's a current pulling this person downstream, and the current is going to push this boat downstream like this. So even though the boat is aiming for this location right here, it is going to actually land, over here. Does that concept make sense there? So the first question I would ask you then, let's just label this right here. The first question is, what is your apparent speed? You in the boat, what do you think you're traveling? 1 meter per second. Is the water pushing you a little bit to the side? Well, yeah, but like if you had like a speedometer inside the boat and the engine of the boat was outputting a certain amount of horsepower, the speedometer in the boat would say you're traveling 1 meters per second. Because relative to the boat itself, that's how fast you're traveling. But that's not actually the line on which you're actually going to move. The boat is still going to face forward the whole time, but the boat's going to go here, and then here, and then here. It's always going to get pushed on a diagonal. Last day in the YouTube video that you were supposed to watch, I had a name for that diagonal. Do you guys remember the physics word for it? Resultant. Good. It does start with an R. Resultant. Good job. And so the resultant would be the actual way the boat is traveling. And so the relative speed, if there was somebody who was standing off here on the sidelines watching the boat travel, the boat is actually going on an angle. But the person who's actually in the boat probably wouldn't even notice that they're slowly but surely drifting out downstream all that much. Does that make sense? So anyways, the long story short is if you want to calculate your relative speed, you'd have to use Pythagoras' theorem. You'd have to take 1.5 squared, add 1.0 squared, and square root it all, and that would get you this resultant. And I went all the way over here without my calculator. That was dumb. I have to go back again. So you actually travel a speed of 1.0. Well, no. You think you travel a speed of 1.0. But due to a 1.5 meters per second downstream current, when I square root it all, I got 1.8 with sig digs. Hopefully anybody else who tested that also got 1.8, right? So that would mean that your relative speed is 1.8 meters per second to the person who's watching the boat right here. But you don't feel like you're going 1.8 because your paddling or your boat is just going 1.0 in this direction here. Now here's what makes this challenging then. Let's say I asked you this third follow-up question. It said, if the river is 150 meters across, how long will this journey take? Well, the formula for this is not a new formula. We're not doing anything above and beyond what we've done before. It's just a twist we have to account for. We're still using the formula V equals D over T because we're going the same speed the whole time, right? Now, if I ask you how long, we're being asked to solve for time. So we have to algebra this for time. So that means time is distance over velocity. Well, okay, the distance I think it said was 150 meters. Is that right? 150 meters? Yeah. But then when we divide by the velocity, here's where the challenge comes in for physics as we go further along. What velocity do we use? Do we use the 1.0 meters per second velocity? Do we use the 1.5 meters per second velocity? Do we use the 1.8 meters per second velocity? I have 3 of them now. Which one would be the appropriate one to use? Anybody have any ideas? Which would be the most appropriate one? Take a stab at it.
The 1 meter per second, because I think that's the direction that
Yes, because the direction that we are actually traveling was straight across, was 150 meters, we should use the velocity that was also pointed in the exact same vector direction. So even though you're actually going to go downstream at a bit of an angle, the velocity we should have used was actually the 1 meter per second because it's the velocity that is going the same direction as the 150 meters that we measured. Right? If we could have measured the distance of this hypotenuse right here, for example, if we did that, then we could use the 1.8 meters per second. So anyways, this one's pretty easy then. If the velocity is 1.0 meters per second, 150 divided by 1 means it's going to take 150 seconds. So, but can you see why this is going to be a little bit more challenging? Is that your perspective matters. Right? And this actually comes up in a lot of other places, not just physics. I'll give you an example from one thing that I taught my grade 9s last semester. When we're studying, like, say, space, and we're trying to figure out what direction stars are in the sky, your perspective matters. If I were to look at this projector right here, from my current perspective, the projector is, I'll even do this. From my current perspective, that projector is to my left. But if I move over here, now it's in front of me. And now if I move over here, now it's to my right. And my location changes how I perceive an object. And so we actually do that in astronomy a lot when you're trying to measure where stars are at. Well, the same thing applies here. If I'm trying to consider how to do the math for this, I have to consider, am I on the boat or am I on the sidelines? Because it makes a bit of a change. The formulas are still the same, though. Does that make sense what I'm saying there? The formulas are no different, but it's how you solve them that changes. Okay, I've got like kind of a, how do you describe this? This is tended to make a point to reinforce what we've discussed. I pulled this off the internet a while ago. I'm sure the times are roughly the same still. I found how long it takes by airplane to go from Edmonton to Toronto. And if you wanted to fly from Edmonton to Toronto, it takes 3 hours and 38 minutes. However, if you want to fly from Toronto back to Edmonton, the same distance, by the way, the same distance, now it takes 4 hours and 6 minutes. Why? Why does it take longer to go west than it does to go east when you're going the exact same distance? Anybody know? Actually, it is not about the way the Earth spins. That's actually a good thought, but it's actually not that one. It's air currents, yeah. Anybody ever heard of something called jet streams? There are actually wind currents that are in our upper atmosphere, the stratosphere, that are always traveling in a certain direction. So imagine that you're traveling with the wind. Wouldn't you be going just a little bit faster? And if you were traveling going directly into the wind, wouldn't that slow you down a little bit? Can't you kind of picture that scenario? Right? Let's just do like a little thought experiment here. Let's say that you could travel on an airplane 400 kilometers an hour. I don't know whether that's the speed or not, but we'll just make that up, right? Well, if you were traveling with the wind, you might get an extra 10 kilometer an hour boost. Therefore, it wouldn't take you as long. But if you were traveling against the wind, so 400 kilometers an hour, but you had to subtract the 10 kilometers an hour, well, in that case there, then you'd be losing a little speed due to that. Does that make sense at all? So I think this is a cool way of illustrating that your perspective matters. The airplane, by the way, thinks it's traveling 400 kilometers an hour. That would be its apparent speed. But its relative speed would either be 410 or it would be 390, depending on whether you're going into the wind or with the wind. Right. Okay, let's try another example here just to kind of illustrate some concepts here. Let's say that you were just sitting in the back of a truck and you just threw a ball right up and down. And I actually brought an apple today just to be my ball. So imagine that I just stand here and I throw the apple right up and down. Okay. If I throw it right up, it's going to land right back in my hand, right? But what would happen if I was in the truck and the truck was moving, right? Well, I'm going to try to diagram that by just walking forward. I'm just going to throw the apple straight up and down, and then I'm going to start walking. Now, from my perspective, I saw this. I saw the apple go up, down, up, down, up, down. That was my perspective. But your perspective hopefully looks something like this. It went up, down like this, up, down like this. Does that make sense how I'm describing that? Perspective makes a difference. To me, I just see it going up and down. Now, as I walk, I still see it going up and down. But you guys, I'm going to diagram this now, should have seen it do basically what this truck was right here, where it went up and it landed right back down in your hand. Right? If you were in motion, the apple is also in motion too. right? This ball right here that this person is carrying here, it's already in motion. And so relative to the truck, it has no new motion. So if you just throw it up and down and you walk forward, I don't actually have to throw the apple in front of me and try to catch up. I just have to just keep throwing it up in the air like this, just as though I was stationary. And it'll always come right back down in my hand again. That's the same kind of concept that relative motion kind of involves. So let's try a math problem on this now. So here's an example. Suppose that you're driving in your car 50 kilometers an hour, and you drop your iPhone out the window. No idea why your iPhone falls out the window, but supposedly it does. You stop your car 6 seconds later. I also tell you the window is 1.4 meters off the ground. The question is, how far behind you is your cell phone once you stop your car? Let's draw a picture of this. I'm not a good artist, by the way. I'm sorry. This is a car. Here's a car. Okay, there's a car. And the car is going to be moving forward, right? Now, what happens if at this moment right here, an iPhone gets dropped? That's a really big iPhone, but let's say an iPhone gets dropped. Will the iPhone be on the ground right below the spot where it was let go? Well, no, because the iPhone itself, relative to the car, has no velocity. But relative to somebody on the outside, is in motion. Can I say that one more time? When you are riding in your car and you're holding your iPhone, relative to the car, it's not in motion. But relative to somebody outside of the car looking at you, it is in motion. So relative to the ground, the iPhone will keep going forward until it gets let go, and then eventually it will kind of fall down and hit the ground like this. So will the iPhone hit the ground directly below the spot where you let go of it? No. It's actually going to have a little bit of a distance that it falls. Now, in the meantime, your car is eventually going to come to stop. Right? Like eventually you go, oh shoot, I dropped my phone, I better stop. So eventually your car's over here. And what we need to do is we need to figure out, well, how much distance is there between the stopped car, I'll use big D for this, and where the cell phone falls. So let me walk you through how to solve this. The formulas are really no different. There's no bonus formulas we're going to use. They're the same ones we've always used. I'm actually going to start by considering the y dimension. Because we know the cell phone is going to fall, right? So the cell phone is going to fall. Why is the cell phone going to fall? Well, because of gravity, right? 9.81 meters per second squared is what's causing the cell phone to fall in the first place. Was it 1.4 meters that I had said that it was above the ground? I think it was 1.4. We know that the cell phone is going to fall 1.4 meters. And then here's one more thing. The velocity initial in the y direction relative to an observer outside of the car, even though the cell phone was traveling in a forward direction, if you drop it, its initial y direction is really nothing. In the y dimension, I have 3 variables. And hopefully by now you guys have started to pick up that if you have 3 variables, that's all you need to get going. So we could solve for velocity final in the y direction, or we could solve for time. Which one's more useful, velocity final or time? Time is. Anybody know why time is more useful than velocity final? Yeah. Well, that's true. Maybe I should phrase that differently. Can you see how I put a little y after all of these variables right here? Why didn't I put a y after this variable right here? Does time only happen in the y direction? No, really, time is independent. You can use time in the x or y direction. If I can figure out how long it took time-wise for this cell phone to hit the ground, it's the same amount of time that it would have traveled in the forward-facing direction, right? Because relative to the ground, the cell phone was still moving forward. So if I could solve for time, that would be kind of a useful value. So I'm going to solve for that one first. I'm going to solve for time. Oh, what am I doing? That's a question mark. Okay, so pick a formula. What formula involves A, D, VI, and T? D equals VIT plus 1/2 AT squared. Again, we're not doing anything new. We've used this formula before. Velocity initial is 0, so you can kind of just ditch this whole section right there because you're dropping this thing. But this is where you have to be really careful. Was the cell phone actually not moving? Well, no, it was moving in the X direction relative to somebody outside the car. It wasn't moving at all relative to the person who dropped it. Right? And it wasn't moving at all in the Y direction. So anyways, that was a 0. If we rearrange this for time, you're going to get 2D all over A square rooted. So if I lost you on that step there and you're not really sure how I algebra'd that, can you let me know? I'll try to give you a math tutorial on that. But basically, this is what we're looking for. 2 times 1.4 divided by gravity. And that'll be how much time it took to hit the ground. Okay, so calculator time. 2 times 1.4 divided by 9.81 square root. And I got a time value of 0.53, etc. I'm planning on using this number again in the future. So do you guys know how to store a number in your calculator? If you're not, again, same thing. Maybe not right now, ask me, but like in the future, can you make sure to ask me how to store a number? I'm going to store this as letter A, just because I have a strong feeling I'm going to use that value again. So let's recap what I've done now. I have calculated how long it's going to take the cell phone to hit the ground in the Y direction. However, relative to an observer watching, this thing is still moving. Let me just do this with the apple again here. Let's say that I were to be walking and I were to accidentally let go of the apple. And let's say that I let go of the apple right here. Would you expect to find the apple on the ground right here when I let go of it? Well, no, because the apple is going to follow a trajectory like this. I'm going to let it go, but it's going to keep moving forward and hit the ground over here. Does that make sense? I'll even drop it today, right? I'm going to let go of the apple right when I'm in line with the Rubik's Cube, right? So I'm going to let go of it right here, and it actually landed right there because it kept moving forward due to its X relative motion. That apple's getting really bruised now. So in the X direction then, we can say this. The velocity in the X direction will always be equal to distance over time. Why can I use the uniform motion formula, you might ask? Like, why do I use that formula? Is anything in the X direction speeding it up or slowing it down? Well, no, gravity affects things in the Y direction, but in the X direction, it would have just kept going on its merry way. So I can use this formula here to solve for distance, that it will travel in the X direction. If I want to rearrange this formula, it would look like this. Velocity in the X direction multiplied by time, which has no direction, would tell us how far the phone moved while it fell, like in this direction. Does that make sense? Okay, well, I know the time value. The time value is 0.53 seconds. Velocity in the X direction, though, was, how fast was the apple moving? Or not the apple, the iPhone. Well, if the car was moving 50 kilometers an hour, so was the person, so was the phone. That makes sense? So relative to the person holding it, yeah, it wasn't moving. But relative to somebody on the outside watching it, the phone was moving 50 kilometers an hour. So I need to make this be 50 kilometers an hour, only there's a huge problem here. Why shouldn't I multiply those numbers by each other? Yeah, the units just don't fit. This was supposed to be in seconds, and that's in kilometers an hour. So I've got to make a change here. There's actually a shortcut if you haven't figured it out by now. You're always either multiplying or dividing by 3.6 as a way of converting kilometers an hour to meters per second. Let me show you that shortcut if you haven't seen it before. If you have kilometers per hour and you want to go to meters per second, hopefully you're familiar with doing this. You'd times by 1,000 meters in a kilometer. And then you're going to say in 1 hour there's 60 minutes. And in 1 minute there's 60 seconds. So let's see, this cancels that, this cancels that, this cancels that. But like once you get the hang of it, you're always using 1,000 and you're always using 60 by 60. Once you figure out the ratio, it's always 3.6 because 60 by 60 is 3,600. And 1,000 to 3,600 is a ratio of 3.6. So if you ever want the shortcut to do this, you could just take 50 and divide by 3.6. And that would actually tell you its speed in meters per second. So I got 13.8 repeating. And then the last step, I need to go kind of back up to here. I'm just going to erase it. I had written 50 kilometers there. However, in meters per second, it was 13.8. So the distance traveled while the phone was in motion relative to the ground. What is that, times by A? I got 7.42 meters. I'm just going to circle that. Does anybody have any questions on that bit so far? Because that actually isn't the answer to the question, unfortunately. I need to go back up to the picture here. What we've now solved for, way the heck back up here, is that it went about 7.42 meters is how far the cell phone, it kind of fell. But I didn't ask you for that. I asked you for how far is it from the car when the car stops, backed up to walk, like when the person has to stand here and walk all the way back and find their cell phone, how far do they have to walk? So that actually I'm still even not there yet. So let's talk about the car for a little while. The car was traveling 50 kilometers an hour. That's its initial speed. And it said the car stopped 6 seconds later. So if I were to, like in my head, make a list of variables, I have an initial speed, 50 kilometers an hour. I have a time value, 6 seconds. But there's one more thing we know about the car. What did the car eventually have to do? It had to, which means we have a velocity final of 0. So we actually have 3 variables. I have to just keep scrolling way the heck down here. But for the car itself, see why it's really important to keep track of who we're talking about? Are we talking about the iPhone? Or are we talking about the car? The car itself had a velocity initial of 13.8 meters per second. The car eventually came to rest. It happened in 6 seconds. Why don't we figure out how far the car traveled? So I just need to use this formula. D equals VI plus VF all over 2 times time. And we have all these. Velocity initial, the car, relative to someone watching from the outside, was traveling 50 kilometers an hour, which is 13.8. Then the car came to rest. And it happened in 6 seconds. So I calculated that the car in that time traveled 41.6 repeating meters. So I'll just make a little note here. This is how far the car went. You might ask, Chris, why didn't we just stop with this? Isn't that the answer? I want to go back up to the picture one more time. I'm just going to wait a second in case you're still writing this down, though. You might be asking, Chris, why didn't we just do this in the first place? That 41.6 meters that we just solved for would have been how far it took once you dropped the iPhone. You see this? From the second he dropped the iPhone is still in the air. Does that make sense? The iPhone is still in the air as he realizes, oh shoot, I better stop. So all the way from here to here was supposed to be 41.6 meters. From here to here was 7.42 meters. So what do I have to do with these two numbers in order to figure out how far back to walk? Subtract them. That's why there was a lot of work to this question. And it was all due to relative motion. If the cell phone literally just fell right below the spot where it was dropped, this would be a really easy question to solve. It would have been 41.6 meters. But because relative to the ground, the cell phone was in motion and it kind of had this free fall right here, we had a lot more work to do. So your final answer, by the way, is 41.6 subtract 7.42. So for anyone who wants to just have the right answer here, 7.42. You get 2 sig digs. So the final answer to this would have been 34 meters. For anybody who wants to know the difference between those two. So as I kind of summarize this particular question, this is where physics starts to go. It's not necessarily about just taking equations and rearranging them algebraically, but there was a lot of critical thinking and problem solving involved in that question, because we actually had to do 3 micro calculations. I had to do well, maybe even 4. I had to do a micro calculation where I solved for time. That was one part. Then I had to do a micro calculation where I rearranged kilometers an hour into meters per second. And then I had to use the time value to solve for a distance. And then I had to solve for a second distance, and then finally subtract them. Now, individually, all of these steps, we've done these already, right? But the problem-solving part is you being able to do that kind of yourself. So, does anybody have any questions they're wanting to ask right now? It's okay if you do, by the way. I know this is not a asynchronous lesson. I'll move on. Okay. If not, ask me later, okay? Let's try another one here. Let's say that there was a jet fighter flying at a speed of 25 meters per second, and it fired a missile at an initial speed of 17 meters per second. I think I made a typo when I wrote this one, because 25 meters per second is not that fast for a jet fighter to be going, but we'll go with it, okay? So the jet fighter is already going 25 meters per second, and then it shoots a missile at an initial speed of 17 meters per second, accelerating at a rate of 2 meters per second squared. I'm going to give you a target, and it wants to know how long. I want to just draw a little picture here. I'm not a world's greatest artist, but like imagine that this is a plane. There's a jet fighter. And it is going to shoot a missile. We'll just pretend this is a missile here. How fast, if I was standing on the ground, would I observe the missile traveling? How fast would an observer on the ground see the missile traveling? Yeah, it's 42 meters per second. Why? Well, because the plane was already going 25 meters per second, right? So when the missile was inside the plane, if I had X-ray vision and I could see inside the plane, I would have seen both the missile and the plane traveling 25 meters per second, right? And then the missile was shot with an initial speed. This is what it really should have said, relative to the plane. Right? Relative to the plane, this is now adding an extra 17 meters per second more, so that it's breaking away from the plane. So an observer on the ground sees it going 42 meters per second. And that's what makes these questions challenging, is you have to figure out which speed to use. You didn't use this speed. You didn't use this speed. In this particular case, you added them together. Now, from here on out, the question's actually not too bad. Let's write out some of the variables we know. We know the initial speed of the rocket compared to the ground is 42 meters per second. We know that it was accelerating at 2 meters per second squared, and I believe it gave you a distance to a target of 800 meters. Well, like I've been saying for the last, 3 weeks of you guys doing physics, you got to get 3 variables. As soon as you get 3, you have everything you need. So I think we were asked to solve for how long, which means we're being asked to solve for time. Now, solving for time, there is one case in which solving for time really sucks, and it's this case here. Because if you used if you used this formula here, I gave it away. You have to use the quadratic formula, which kind of sucks. You can do it, but there's ways around it. Like you could make this number be 800. You could make this number be 42 times t. You could make it 1/2 of 2 times t squared, and you could use the quadratic formula. And if you feel comfortable with that, go for it. Let's say you're not really loving the quadratic formula. You don't have to. There are other ways around it. Solve for the other variable, because we could, in theory, solve for velocity final. Why don't we just do that instead? I know we don't ultimately want velocity final, but this should work out the same way. Why don't I, rather than using the quadratic formula, rather than doing that, let's just pick another formula. Let's do Vf squared equals Vi squared plus 2AD. And I'll square root everything here. Let's find velocity final. Velocity initial relative to the ground was 42 meters per second. It was accelerating at a rate of 2. It has to travel for 800. Let's find the final speed of this thing. So this would be the speed of the rocket as it hits the bad guy's layer that you're trying to blow up, I guess. So I got to 70.45, something like that. Meters per second. I'm going to store that as letter B, because we're definitely going to use this again. Okay, now, I didn't actually want velocity final. However, now that I have a different set of variables, so now that I actually do know the velocity final, I can just pick another formula that solves for time, and now I don't have to use this formula, because that formula kind of sucks for solving for time. Why don't I just use a different one? Like, for example, this one here. How about D equals VF plus VI all over 2 times T? Let's use that formula. Do I know the distance? 800. Velocity final, it's right there. Velocity initial was 42, and times what I'm looking for. So just algebra this one instead. Saves you the quadratic formula if you don't want to. So I'm going to do the math first, though. It's going to be 2 times D over VF plus VI. That'll get you T by itself. So 2 times, what was it, 800? Velocity final, I have now made letter B in my calculator. And velocity initial was 42, I think. So there, this will give me my answer. 2 times 800 divided by letter B plus 42. I got 14 seconds. So again, the formulas weren't new formulas, but what I think a lot of students would struggle with is as they look at this particular question here, they see a speed right here, and they go, oh, maybe my speed is 25. Or they see a speed right here of 17, and they think, oh, maybe my speed is 17. It was neither of them. In this particular example, we had to add them because the speed that the rocket had got to add on top of the speed of the plane. Let me just discuss terms again. Relative to the ground, the rocket was going 42. Relative to the fighter jet, it was going 17. More than the fighter jet was going. Does that make sense? Your perspective makes a difference. Anybody have any questions on that one? Yeah, for sure. Yeah, how far? To like the very bottom? For sure, I can do that. Anybody else have questions on that? Okay, I have one last example. Before I give that last example, I want to give kind of another analogy here. Can I flip the slide? Is anyone still ready? Okay. Before I get to this last example here, I want to kind of present another sports scenario, because I love sports scenarios. I always do those. Imagine that you're a football kicker, and the football kicker is lined up, and they're about to kick, here's the football on the ground. And they have to kick at the field goal posts way over here. So this is kind of your perspective here, I guess. Does that make sense so far? And so the field goal kicker wants to kick the ball basically in a nice straight line through the field goal. And I know it actually arcs like a parabola, but let's just pretend it's going in a nice straight line, right? However, let's say it's a really, really windy day. Like so windy that, for example, the wind is blowing this way, pretty hardcore. Well, if the kicker aims right here, and it's really windy, it's going to push the ball, and the ball will actually go way off course. You know what I'm saying there? So where should the kicker actually aim, knowing that it's really windy? The kicker maybe should aim over here, aim for the ball to go this way, then when the wind pushes it, it goes through the middle of the field goal posts. Does that make sense? And that's also apparent and relative motion. Because if you were riding on the football, somehow we're on the Magic School Bus, Miss Frizzle zooms us down to size. If we were riding on the Magic School Bus on this football, you would think that you're traveling this way right here. but you wouldn't realize that an external force is pushing you off to the side, and so relative to the ground, you're actually traveling a different way. We can actually do triangle type questions with the exact same concept. So last day in the YouTube video I showed you, hopefully you guys solved a question where you were kind of heading this way, and then maybe it pushes you this way, and the net resultant goes like this. Hopefully you guys saw questions like this, because that's what we're going to solve as well here, is that you want it to go this way, but the wind pushes you this way, therefore your resultant pushes you off course. That's what this final question is about. So let me set this one up now. A plane needs to travel 350 kilometers due west. So let me draw that out here. The plane needs to travel 350 kilometers directly west. So we'll make this west. And it has to do this in 2.25 hours. So there's a timeline, basically. I'm going to pause right there. Could we not figure out the speed of the plane then? I mean, if we know it's kilometers, we know it's hours, couldn't we find the speed of the plane? Assuming it's traveling the same speed the whole time. So 350 divided by 2.25 means that this plane is actually traveling 155.5 repeating kilometers per hour. So I know how fast the plane needs to travel. But here's the problem. Don't draw this next section, by the way. I'm going to make an error on purpose. So if you're following along, please don't draw this. But we know there's a wind. And the wind is going 65 degrees north of west. What that means is that if I don't deviate my travel plans, the wind would push me 65 degrees up here. And so if I didn't deviate my travel plans, I would actually end up over here. Not only would I be pushed to the side, but I would have overshot my target. Does that make sense? So I have to account for that. This plane would actually have to reduce its airspeed. You know how I just said its airspeed was supposed to be 155 kilometers an hour? It's going to have to travel a little bit slower. Because if it travels this speed, it's going to go too far. So it better travel slower instead. And not only that, it doesn't want to aim for right here. We actually want to aim for a location right about here instead. So rather than aiming due west, what we should actually do, you guys can probably start drawing this if you'd like now. We actually want to aim. Ooh, can you guys see yellow that well? I don't like yellow. Let's try pink. You're actually going to want to aim for this direction right here so that, hopefully this works here, when the wind pushes you off course, you end up in the right spot. See how cool that was? If you, oh, I didn't want to pick that one up. If you do go the straight direction, if you aim right here, the wind would push you off course. But if you actually aim slightly to the side, you'd actually end up in the right spot. How is this different than the field goal question, right? If I wanted to kick a field goal straight on, but I knew that I was going to get blown to the side, I don't aim straight on because I know it's going to miss, right? I aim over here, so the wind pushes it back again, right? Well, now we basically have a scenario like we had yesterday, where we've got triangles to work with. Now, if you know how to use the cosine law, you can use the cosine law. I'm going to use all those little micro calculations by doing sine and cosine kind of calculations. Let me write some stuff out here. Right here, there's a little triangle. You see how there's a little triangle kind of hidden in here? I'll draw it in red. And why don't I call this side right here y1, and this side right here x1. Now there's also a triangle in the one that I was aiming for. I'm going to make a triangle out of this guy right here as well. Why don't I call this side here y2, and this side over here x2. And in this particular example, I don't actually need a third triangle. The reason why I don't need a third triangle is that the top vector that I'm working with, it's already completely flat across. So I don't really need to worry about it. But I should label it. Why don't I call it x? Because it's going in the x direction, right? I'll just call it x3, I guess. So this side right here, I need to end up going 155 kilometers an hour on this side right here. That's going to be my relative speed to the ground. But this is what this person here is going to have to aim for. The pilot is going to have to aim to go a little bit short and to the side so that the wind pushes them back where they want to go. Right? So this is actually going to be their apparent amount. This is what they're going to think they're doing. The airplane thinks they're going to go here, but no, that's not what's happening. You're actually going to end up. Does that make sense? So anyways, let's solve the question. I think I'm going too slow. We also know, by the way, that this side right here was, what was it, 40 kilometers an hour? So I'm going to write a few statements out here. The first one I'm going to write out is that I know what x3 is. x3 was 155.5 kilometers per hour. I knew that one. Why don't I figure out x1? Now, if you're lost on this step right here, because I'm going to do a couple of shortcuts, can we talk later? But the best way of writing x1 would be to write 40 cosine 65. And that would make y1 40 sine 65. If you're lost on that, can we chat later? Can you make a point of coming to talk to me? I mean, the short version, like the 30-second in class version, is that this was the hypotenuse. This would be the opposite. This would be the adjacent right here. And so when you're looking for the adjacent, which is x, adjacent is cosine. And opposite is what sine is. So I may as well find those values now. So 40 cosine 65 is 16.9 or so. And 40 sine 65 is 36.2. Any questions on that? Okay. Well, I'm ultimately looking for this purple pink side length over here. To find that, I need to know what y2 and x2 are. Well, why don't I start writing that out then? I want to find x2, I want to find y2. That's what I'm ultimately trying to look for. This is where you have to do all those little micro calculations, right? All these little bits and pieces. What is y2 going to be equal to? When you look at this shape, y2 is how far it is from here to here, right? What else is that exact same distance? y1, yeah. Isn't this the exact same amount from there? So y2 really equals y1, which is 36.2. What about x2? Using some shape theory, if x2 is from here to here, how could I calculate that? Yeah, this one here is the big one, and you'll have to subtract this one over here. So it's x3 minus x1, right? It's the whole long length of 155.5. So I have to take 155.5, and I have to subtract 16.9. So I'm going to try to do that as exactly in my calculator as I can. So I'm just going to redo this. It's 155.5 minus 40 cosine 65. I'm just going to store this number in my calculator. So I got about 138.6. But I'm going to store this as A, and I'm going to try to store this one as B, just so I have these values stored here. So store that one as A, and then 40 sine 65 is going to be stored as B. Okay, so last step here. If you're able to follow along here, we now know this side right here. We now know this side right here. What I was really looking for was, well, what speed should you actually travel? Will this guy need to travel 155 kilometers an hour as his apparent airspeed? I think it's going to be a little less. He's only going to need to travel 140 something because the wind is going to push him back up to the 155 mark, right? So long story short is you got to use Pythagoras' theorem. You got to do a squared plus b squared equals c squared, and square root it all. So a squared plus b squared square rooted. I got a final answer of 143 kilometers an hour. And that kind of made sense to me, because the plane's apparent speed, the plane thinks it's traveling 143 kilometers an hour, but it's not, because the wind is giving it a bit of a boost, and so its relative speed was actually 155. Let me say that one more time. The plane thinks it was traveling 143. It wasn't. The wind was giving it a boost. So its apparent speed was 143. Its relative speed, though, would have still been 155. It also had to aim down here at the corner, right? It had to aim at a different location so that the wind could push it back again. Does that make sense? Cool. Technically, to do this right, this had 4 sig digs, this had 3 sig digs, this had 3 sig digs. This right here had 2 sig digs, which means if we're actually doing this properly, we should keep 2 sig digs. So we should actually make it like 140 kilometers an hour, or make it 1.4 times 10 to the 2 kilometers an hour. That's how we should technically do it. So that's, I think, all I've got. That was my last slide, right? Yeah. Ooh, let's scroll that back down for anyone who's still writing. Okay. Questions, comments, concerns, conundrums, curiosities, criticisms, complaints, queries. I think I'm out. How'd that go? Does that make sense? Can you follow that? Yeah. Yeah. Oh, good call. Okay, so I was a little lazy, wasn't I? Kilometers per hour, yeah. I mean, if we were writing units, which we probably should be doing, they were all kilometers per hour units. Good call. Thank you. Anyone else have questions, ideas there? Yeah. You can. Okay, so here's a good point. I mean, there are multiple ways of solving things. If you know how to use cosine law, you could do that. Let's talk about how you would have done that, though. In order to use cosine law, you would know this side right here. You would know this side right here, and you're looking for that side. It means you need to know this angle right here between them. So to know that angle, you'd have to know like some basic like trigonometry. If this angle right here is 65, that angle there was also 65. So in theory, you could have done c squared equals a squared plus b squared minus 2ab cos 65, done it in one step. Yeah, good call. I will say this though, cosine law and sine law, they don't necessarily always work. There are some scenarios where they don't necessarily work. Let me give you a good example here. Let's say that I made a scenario where something was going this way, then it went this way, and then it went this way again, and you had to find the hypotenuse. See how that wouldn't be a three-sided object? Then you'd actually have to break this up into this triangle, to this triangle, to this triangle, and to that triangle. That was kind of a weird way of me drawing it. Let me do a better one here. Let me try this again. Let's say that you went this way, then you went this way, then you went this way, and then I wanted you to find the resultant. Do you see how you couldn't use the cosine law now? But what you could do is make a triangle here, make a triangle here, make a triangle here, make a triangle here, and go y1, x1, x2, y2. Kind of see how you can piece it together? So I can't guarantee cosine law always works, but it is a good shortcut if you can see how to use it. Okay, cool. Okay, let's do one last thing here, and then we'll have some pack-up time here. I want to show you guys your assignment. Yesterday I talked a little bit about the Mythbusters project. Today I'd like to talk to you guys about your second assignment. You don't have to do it. Okay, if you guys have looked at my progress log, the second assignment can be worth nothing. Okay, you should do it. Okay, like just a piece of suggestion. I didn't make the assignment just for fun, but like I don't want to put a lot of stock into worksheets. I like to give you things other than worksheets, but it's not a bad idea to do a worksheet once in a while. So here's your second assignment. I want to talk to you about a couple of questions on it. So here's assignment number 2. Okay. So let me zoom in here. Let's read along. The first question here is the Daytona 500 is a NASCAR race consisting of drivers completing 200 laps totaling 500 miles. Now here's the scenario. Due to a crash on the course, a driver ends up a full lap behind the lead car. Therefore, he needs to have a higher speed in order to catch up. Now, are all the cars that are ahead of you just going to stop because you fell behind? Well, no, right? So you're going to have to drive faster. I think everyone gets that. But here's why relative motion matters. I'm going to tell you that the lead car traveled 138 miles per hour. I'm going to tell you that the car that fell behind traveled 143 miles per hour. when you solve this question, you're not going to use 138 miles per hour. You're also not going to use 143 miles per hour. What is the speed you're going to use? Anybody know? 5. 5. Because that's the difference between the two of them, right? Relative to somebody watching, this guy's going 138. Relative to somebody who's watching, this guy's going 143. But relative to each other, this guy's going 5 miles an hour faster. So like when you solve this question, you're actually going to solve it using 5 miles per hour as your velocity, because that's how much he makes up at a time. Does that make sense? Okay. I'm going to show you another question here. The Tom Brady question we'll do after Thursday's notes. I'll do that one next. Let's do this one here, the canoeist question. Let me read this one here. There's a canoeist who's trying to paddle downstream, or trying to paddle against a downstream current of 1.5 meters per second. And despite this current, he still manages to travel at a velocity of 0.8 meters per second upstream. So I just want to make sure you understand the scenario. There is a head-like current coming directly in your face. And if you don't paddle at all, you're going backwards. But this guy paddles so valiantly that he manages to go upstream regardless of the fact that the water is trying to push him back downstream. And then I'm going to ask you, what is the speed the canoeist could have paddled on flat water? I hear it. That's right, yeah. Because it's really adding these two numbers together. Maybe here's one way of thinking about it. If you could travel 2.3, you would have. But the 1.5 is going to pull back against you, and therefore your resultant, or your net value, will be the 0.8 you managed. See how that works? 2.3 is how much you did paddle. Your apparent speed was 2.3. But you got pulled backwards by 1.5, so therefore your relative speed was 0.8. Boy, that's like, it's tricky to talk about that, hey? So what makes this next part of our unit so challenging is that the math calculations, same formulas we've always done, but you have to have really good interpretation skills. Okay, let me do one last one and I'll call her quits here. This is just like the one we just did. I'm going to stand in front of the board here. There is a ferry that's going to go from Comox to Powell River, so it's going to go from here to here, from Comox to Powell River. But it says that there is a river current traveling 3.6 kilometers an hour at 300 degrees. If you guys know your 300 degrees, 270 is straight down. So 300 degrees is basically pointing somewhere towards, like, say, Hornby Island. So there is a river current basically going this way right here. Okay. Now, if they go from Comox to Powell River and the captain aims at Powell River and the current goes this way, they won't get to Powell River, will they? They'll end up crashing into this island right here. Does that make sense? So what the question is really suggesting is, where does the captain have to aim? Determine the velocity that the ferry should intend to travel in order to make this work. So the captain's going to have to aim up over here, right? The captain's going to aim at this location so that the ferry gets pushed back down to Powell River. Does that make sense? Now, I want to make sure it's clear, though. Will the ferry actually travel this way than that way? No. That the ferry will actually travel along this path, but he has to aim that way. So the apparent speed would be this way, and then the relative speed would be the speed he actually travels. So anyways, I've got some practice questions for you guys to try, because you need some practice, right? Like, I gave you a lesson now. Hopefully you had questions. Maybe you didn't want to ask me right now, but like, you need to do some practice. So tomorrow's goal is I want you guys to work on 2 different things. 1, I want you to start working on the second assignment. And 2, can you guys think about that Mythbusters project? You can work with a partner. You can work with a group of 3. You can choose any movie you want. Okay, I don't care. You could pick the Avengers movies for all that I care. But you need to find some sort of scene that you think is kind of cool, that you think you can try to calculate distances and velocities, and you have to estimate them. If you're really stuck, just pick one of the movies I suggested, like Back to the Future or Spider-Man. Okay? That's our goal tomorrow, to work on one of those 2 topics. And then on Thursday, can you guys make sure you bring some headphones again on Thursday? Because although I do like teaching you guys like this, sometimes I think it's better if you can just go at your own pace. Because I got to be honest, I'm sure I probably bored a few of you today, because you're like, Chris, speed it up. And a few of you might have been like, Chris, this is way too fast, slow down for me, right? So, does that work? Okay, cool. We have like 10 minutes left in class, so kind of work on whatever you need to in the next 10 minutes here. And we'll chat again tomorrow.